Hey, welcome back to Calculus, Calculus 2. This is the second video lecture from section 10.2 on calculus of parametric curves that are given parametrically. Last time in the first part of this, we looked at how do you find slopes, how do you find tangent slopes and equations of tangent lines to curves that are given parametrically. In the current lecture, the second one of this section, we're going to look at two more goals. One of them is how do you find second derivatives for functions that are given parametrically? That is, how do you describe concavity, right? And then I want to show you how you can calculate the area of certain regions that are enclosed by parametric curves. Okay, so those are our two goals. Let's get right to it. Second derivatives. Okay, well, what did we see last time? Last time we saw that if you're given two parametric equations, x of t and y of t, then to compute the derivative at any point on the curve, dy dx, to find the tangent slope, then you take the ratio of dy dt to dx dt. So again, it's kind of a nice formula to remember. It says that the slope is the change in y over the change in x. It's just that here, I mean, change in means derivative. All right. So now I want to find second derivatives. Okay, well, what's a second derivative? It's the derivative of the derivative. So we really don't need a new idea. All we have to kind of notice is that this first derivative, it's also a function of t. Yeah, if you've done your homework from the first part of 10.1, or you looked at some of those examples I did, or the activity, then you'll notice that whenever you calculate the derivative of a curve given parametrically, you get that derivative expression in terms of t. So if you want to know a second derivative, well, we just have to differentiate again, thinking parametrically. So if I scroll down here a little bit, you'll see what I mean. If I want the second derivative, that's the Leibniz notation for it. D squared y dx squared, I just mean second derivative. Second derivative. And how do I calculate the second derivative? Well, I do it parametrically. So I take the change in the function with respect to t of the first derivative. Yeah, that's how we calculate parametric derivatives. That's the y part, if you like. And then we have to divide that by dx dt. So it's exactly the same kind of formula as what's going on up here. It's just in the numerator, the thing I'm differentiating is no longer y, but it's dy dx, because I'm trying to calculate the derivative, the second derivative, sorry. Why am I doing it like this? Well, because it's given parametrically. I have to do everything in terms of t. So I take the derivative of dy dx with respect to t. I take the derivative of x with respect to t. I take the ratio in the same order. That's the main result. That's it. That boxed formula tells you how to compute second derivatives, functions given parametrically. Let's do an example. Let's see an example, and then you can practice yourself. So for the example, I want to recycle the one that we looked at in the last video, because we've already computed its first derivative and we're kind of looking at its graph. I like its graph. I like the shape of it. So I'm going to take these same two parametric equations that we looked at last time. X is t cubed minus 3t, y is t squared. Let me scroll down here a little bit. Maybe you can partially see the graph. Look familiar. We can indicate on here, we did it last time, that this curve is sort of swept out this way. It's another chance for you to practice if you're still grappling with that. But this curve gets swept out like that as t increases. So I want to calculate the second derivative. All right, I want to calculate the second derivative. We're going to use this formula. We need to take the derivative of the first derivative with respect to t. Well, we did that computation last time, although for this example, I think it's simple enough. dy dx, we can just recapitulate it. Dy dx is, well, it's dy dt. 2t, that's certainly the derivative of t squared, divided by dx dt. 3t squared minus 3 is certainly the derivative of t cubed minus 3t. So there's our first derivative. Okay, so to calculate the second derivative, that's the thing we need to take the derivative of. We need to take the derivative of dy dx with respect to t. And it makes sense. Look, it's a function of t. It's 2t over 3t squared minus 3. All right, so that's what I'm writing here. Take the derivative of that thing with respect to t. D by dt of dy dx. It just means differentiate it. So take d by dt of this thing. And dramatic pause in the video. What rule do you have to use? It's been a while. since we've done differentiation that's this complicated. But what rule is that? That's the quotient rule, people. Yeah, taking the derivative of a fraction, I got to use the quotient rule. So that's what I'm doing here. Let me just kind of walk you through the quotient rule. You square the bottom of the fraction, you take that bottom times the derivative of the top. The derivative of the top is just 2. And then you subtract the top times the derivative of the bottom, which I hope you agree is 6t. All right, and I wrote this out beforehand, but you can stop and do this yourself if you like. I'm just doing some algebra. All I did in this numerator is distributed out, multiplied the terms. That's it. Nothing happened in the denominator. Then I gathered some like terms. I didn't really show you every step, I guess. This 6t squared and minus 12t squared would make a minus 6t squared, and I factored that minus 6t out, or minus 6 out, rather. So check my algebra. I'll let you do that at your own pace. All right, so that's the derivative of dy dx with respect to t. Remember, dx dt, we already calculated. It's 3t squared minus 3. So you want the second derivative. Okay, you take the derivative of dy dx. That was the long quotient rule calculation. You divide it by dx dt. A little bit of algebra simplifies that thing into that expression. Cool. That's it. That's calculating a second derivative of curves given parametrically. It's often the case that the quotient rule is involved. Why? Well, because dy dx is dy dt over dx dt. It's almost always a fraction, unless you can simplify it somehow first. Cool. All right. Well, let's take a second to kind of remind ourselves. What do you do to second derivatives? Second derivatives describe concavity. Yeah. Second derivatives describe concavity. We've got a nice expression for it here. I went ahead and made a sign diagram for this second derivative. So let me remind you a little bit about that. In a sign diagram, I want to mark any points that make the function, in this case, the second derivative, d squared y dx squared, 0 or undefined. If you look at the numerator of this function first, the numerator of this function is never 0. T squared plus 1 is never 0. And if you multiply a non-zero number by a -6, you're also not going to get 0. So there's no way that this thing is ever equal to 0. The only way that we could have critical values of this function is when the denominator is equal to 0. When the denominator is equal to 0, you can check if and only if t is plus or minus 1. 3t squared minus 3 is 0 if and only if t is plus or minus 1. You can do that by factoring or just kind of thinking about it. So that's what I've marked here in my sign diagram. I've got those two values, plus 1 and minus 1, and those little dot, dot, dots just remind me that those are values that make the second derivative undefined. Okay? And then what did I do? I picked numbers, numbers that are less than 1, numbers that are between minus 1 and 1, numbers that are bigger than 1, and I plugged them into the second derivative. And I just recorded where the signs were positive or negative. So I'm going to leave it to you to kind of verify my work here, but I'm claiming that if t is less than minus 1 or bigger than 1, the second derivative is negative. And if it's between minus 1 and 1, then the second derivative is positive. And you guys remember that positive derivatives, second derivatives, mean that that's where the function is concave up. Places where the second derivative is negative, the function is concave down. Oops. Getting a little messy there. Concave down. Yeah, where on the curve? Well, we're given all this information, and it's always this way parametrically. You're always given information in terms of the parameter. T is minus 1, T is 1. If you want to know where you are on the curve, well, you got to use the parametric equations to answer that. So I'll let you check the arithmetic, but like this first column, I just took the number -1, I plugged it into x, I plugged it into y. So when t is -1, I'm at 2, 1 in the plane. So I can visualize that. 2, 1 is sort of this point on the curve. Sorry, wrong color. T equals, let me fix that. 2, 2, 1. This is where I'm at when t is -1. When t is 1, I'm at -2, 1. It's over here. All right. So let's again look at this sine diagram, saying the function is concave down when t is less than -1, and then again when t is bigger than 1. So we know the direction of the curve. We can just shade on this thing. It looks right to me. T is less than -1 up to there, and then t is bigger than 1. And do you guys agree that over both of those sections that I just highlighted in red, the curve is concave down there? It's absolutely right. What about t between -1 and 1? Well, starting at -1, here's where t is equal to 1. It looks concave up there. Pretty cool, huh? So the second derivative is the thing that's describing the concavity. Let's take a look at the area problem next. Area. The area problem, the usual picture here. I've got some function y equals f of x. Drawing a curve there. I want to calculate the area below it. Well, in Calc 1, you were taught that the area is calculated by taking that integral, or if we rewrite y, take the integral of y with respect to x from a to b, you calculate that area. Well, let's suppose that that curve, this curve up here, y equals f of x, is given parametrically. So it's given by x and y, two functions of t in some range. I can't use a and b again, so I went Greek on you. I'm using alpha and beta. So that parametrizes the graph. Parametrizes the graph. I didn't write an indication of the direction yet. Hold on for a second. Okay, so how do we calculate this area? Well, the area is the integral from a to b of y dx. Well, a y we can replace with y of t. And what's dx? Well, if x is x of t, then dx is, well, take the derivative, x prime of t dt. I'm just writing that in differential form. So that's why my dx down here gets replaced with this x prime of t dt. And then what about these new limits of integration? Well, when one possible case is that when t is alpha, x is a, and when t is beta, x is b. In that case, this curve would get swept out in the left to right direction. In that case, this thing gives us the area. That's our second and final main result. If you want to find the area of a curve that's given parametrically, if it's swept out from left to right as the parameter increases, then you would calculate it by integrating y times x prime of t dt. Okay? Well, what about in the second case? Let me actually sort of change the second case's color so that we can see it. The second case, get rid of that and write it in blue. In the second case, the only difference is that when t is alpha, x is b, and when t is beta, x is a. So that exactly means that in the second case, the curve is getting swept out this way, from right to left. Well, so area is still the integral of y dx, but this time notice the limits of integration. Alpha ends up on the top, beta ends up on the bottom. It's because of that orientation switch. It's because we're traversing the curve left to right. But this number, when you calculate it out, this integral, keeping the limits of integration in the correct order, it'll give you the correct area. All right, let's do a quick example and then we'll end this video. If you watched the video on the derivation of the cycloid, and I hope you did, then these equations will kind of be a little bit less unfamiliar. But the cycloid curve here, the path traveled by a point, fixed point on a wheel as it rolls without slipping, is parametrically given by t minus sine t and 1 minus cosine t. I want to just take one revolution of the cycloid. T goes from 0 to 2 pi. And here, the radius of my wheel, if you're curious, it was 1. I just set the radius equal to 1. Okay, so this curve is parametrized in such a way that its direction is left to right. So the area is just going to be integrate over the parameter space in that order, 0 to 2 pi. If the curve were swept out from right to left, I would have just switched those limits of integration. That's it. And then I got to plug in the pieces. Okay, well, y of t is 1 minus cos t, so I put that here. X of t is 1 minus sine t, so its derivative, or excuse me, t minus sine t, so its derivative would be 1 minus cosine t, and those are the same, so this is the function that we need to integrate, and then we'll finish this thing out by writing it out as we go. All right, so how would you integrate this thing? I would personally, I'm going to kind of bring it over here so we have some more room, just expand out 1 minus cosine t squared. So we'd have a 1, we'd have a minus 2 cosine t, we'd have a plus cosine squared t, and then I would just do those three integrals separately. Um, integrate from 0 to 2 pi 1 dt, take away 2 times the integral from 0 to 2 pi of cosine t dt, and then add the integral from 0 to 2 pi of cosine squared dt. All right, each one of those is handleable. Let's start handling them. The integral, the antiderivative of 1 is just t. So you're going to evaluate that from 0 to 2 pi. Here, I could do it. The antiderivative of cosine is sine. Well, let me just do it. So I have sine of t, negative 2 times it from 0 to 2 pi. And then what about this guy, the cosine squared? Well, we have to use that identity. You have to use that trig identity. That's 1/2. The cosine squared is 1/2 1 plus cosine 2t. Okay, so that's not a done integral yet, but we can start on the next line. Here we get 2 pi take away 0, evaluating that. Minus 2 times the sine of 2 pi is 0, and so is the sine of 0, so that term is just gone. And then here, a little bit of anti-differentiation to do. We have to anti-differentiate the 1. We have to anti-differentiate the cosine of 2t. It's 1/2 sine of 2t. Okay, so one more evaluation. What do we got here? 2 pi, take away, well, 0, plus 1/2. When we plug in 2 pi for t, we're going to get 2 pi plus 1/2 the sine of 4 pi. That's 0. Take away 0 plus 0. All right, so it looks like we got 2 pi plus 1/2 of 2 pi is pi. The area under one hump of that cycloid, one bump of our curve, is exactly 3 pi. All right, I'm going to end this video here. I hope it was instructional, and I'll see you in class. Thanks for watching.